Okay. So last time we discussed the definition of being a positive or negative definite. That being a positive or negative definiteness of a real symmetric matrix. Okay. So a real and symmetric matrix is positive definite if and only if x transpose times a times x is positive for all non-zero vector x in Rn. Okay, so this is definition. So, and being positive or negative definite is very much to do with something to do with a local maximum or local minimum of differential functions. So, well, so for if your function is twice continuously differentiable, then for any function, for any point p, then you can define a n by n real symmetric matrix which is called the Hessian. And on top of that, if the point is a local critical point, then your function, the point is a local minimum if and only if the Hessian matrix is positive definite. And the critical point is local maximum if and only if the Hessian matrix is negative definite. Okay. Okay. So the natural question is, how do you know any given n by n real symmetric matrix is positive or negative definite? Actually, we have a partial solution of the question. So in the case when A is 2 by 2 matrix, when A is 2 by 2 matrix, A, B, B, and C, then being positive definite was the discriminant was negative and the leading coefficient positive, right? So A is positive and the discriminant, which is AC minus B squared, is positive, right? Yeah. So this is the criteria that tells us that if any given 2 by 2 real symmetric matrix is positive definite or not. So, okay, but what about some n by n matrix with higher size, the higher dimensions? Today, so we want to discuss about the test for positive definiteness. So that means, suppose that for any given n by n real symmetric matrix, so we want to have some sort of criteria which tells us that that matrix is positive definite or not. Okay. I guess this theorem is the biggest theorem in today's lecture. Okay, let me try to read it one by one. I have a matrix A, which is n by n, and that is also real and symmetric. Then the following four statements from number 1 to number 4, they are all equivalent. Okay, so number 1, A is positive definite, and number 2, all the eigenvalues of A are positive. So I need to explain something about number 2. Well, so since A is since A is real and symmetric, that means A is real and symmetric. That means because of the spectral theorem, so A can always be orthogonally diagonalizable, right? And its eigenvalues must be always real, right? If your matrix A is symmetric, then you cannot have complex eigenvalues. So your eigenvalue is always real. So, and if A is positive definite, then number 2 says, if and only if the eigenvalues of A must be always positive. So you cannot have 0 or negative eigenvalues. Okay, and number 3. The statement number 3 is about the principal submatrices. So what is the principal submatrices? Well, if this is your n by n symmetric matrix A, real symmetric matrix A, then the principal submatrix is it can be obtained by drawing a square, which is starting from the top left corner of your matrix. And if you draw the k by k sized rectangle square from here, then all the matrix that you can find in this square is called the principal submatrix, which I will call AK. Okay. So if the size of your matrix is n by n, then you are supposed to have the n many principal submatrices from A1 to AN. A1 is just nothing but just the one entry of your matrix, and AN is just A itself. Okay. And number 3 tells us that A is positive definite if and only if the determinant of each of these n many principal submatrices are all positive, right? So you compute the determinant of this guy and this guy. So you compute the determinant of n many matrices, and if they are all positive, then that implies that A must be positive definite. Okay. And number 4. Forward elimination can be done without row exchange, and all the pivots are positive. So, and the last assertion is also, yeah, it sounds very useful. Well, so A being positive definite, if and only if, well, you can apply the forward elimination towards the matrix A, and if the pivots are all positive, so if the diagonal entries of the resulting upper triangular matrix is all positive, then that implies that A is a positive definite. Okay. All right. So I will try to prove one by one. So since this is, well, so I am supposed to prove that they are all equivalent. So I gotta prove many theorems, but well, okay, let me just begin. So from number 1 to number 2. So well, let us assume that A is positive definite. Then lambda is an eigenvalue of A, so that means A times X is lambda times X. And I multiply the AX transpose to the left side of this equation. So X transpose times AX is lambda times XT times X, but XT times X is just the length of the vector X. And because we are assuming that A is positive definite, so this number is also positive. So therefore, the lambda also must be positive. Okay. And from number 2 to number 1. So I'm proving the opposite direction. So if all the eigenvalues are positive, then A must be a positive definite. Okay. Well, you also have to remember that. So any real and symmetric matrix allows a diagonalization. And in that case, you can choose your eigenbasis to be orthonormal basis, right? So we say, in this case, we say the AK is orthogonally diagonalizable. So by the spectral theorem, so the vector space Rn has a orthonormal basis consisting of eigenvectors of A. So I'm going to name it. So these eigenbases, I'm going to call from Q1 to Qn. And so this is basis. So every vector X can be written as a linear combinations of these vectors, these basis vectors, like this. From C1, Q1, Cn, Qn. Now I try to compute xt times A times X. So this is xt times A times another X over here. But since Q1 to Qn they were assumed to be eigenbases, eigenvectors. So multiplied by the matrix A. So these Q1 to Qn is they are all now lambda 1 Q1 to lambda n Qn. Okay. So now this guy times that. So I am taking the inner product of these two vectors. And there's very nice news because the Q1 to Qn, they are assumed to be orthonormal bases. So I can make use of the Pythagorean theorem, right? So this guy times this, but Q1 transpose Q1 is just 1. So eventually I have C1 squared times lambda 1 and C2 squared times lambda 2. So and Cn squared times lambda n. So this is something more like the component-wise multiplication and summation. Okay, and the statement number 2 was assuming that eigenvalues of A are all positive. So lambda 1 to lambda n, they are all positive numbers. So therefore, this guy is always non-negative. Okay. And what is under what condition this equality is true? This equality is true if and only if C1 from Cn they are all 0, right? Because lambda 1 to lambda n they are assumed to be always strictly positive, right? So this guy equals to 0 only if C1 to Cn they are all 0. But C1 to Cn they are all 0 implies that X is a 0 vector. So in other words, this equality is true only if X is 0 vector. So that implies a matrix A is positive definite. Okay. Great. All right. Now I want to prove the statement number 1 implies statement number 3. So, hey, what was number 3? Oh, number 3 was about the principles of matrices. Oh, okay, great. So we are assuming that A is positive definite. So therefore, for every vector, for any vector X, no matter which vector you plug in here and there, then the number must be always non-negative, right? But instead of plugging in any random vector in these two positions, but I decided use this very special vector. So what makes this vector so special? So the entries of these vectors, there's possibly non-zero numbers from x1 to xk, but after the case entry, all the other entries equals to 0. So I plugged in these vectors in here and there. And again, we are assuming that A is positive definite, so this number must be always non-negative, right? But multiplying this times this is the same as multiplying this k-dimensional vector to k's principal submatrix AK times the same vector, right? Right? And this is also non-negative. And also this guy equals to 0 if and only if x1 to xk equals to 0, right? So that implies this principal submatrix AK is also positive, right? Okay, good. So okay, so AK, so A1 to AN, they are all positive definite matrix. And now let me just go back to our previous proof. So we have proved that a matrix is positive definite if and only if their eigenvalues are all positive, right? So eigenvalues of each of these principal submatrices must be also all positive, right? And you also need to remember the determinant of any matrix is just multiplication of all eigenvalues, right? And since eigenvalues of AK is all positive. Therefore, determinant of AK is also positive, right? So determinant is product of all eigenvalues of AK, and which is positive, right? Okay, good. Okay, so now I am proving that number 3 implies number 4. Number 4, yeah, number 4 is about the fourth elimination. Okay. To prove this, then I want you to remember this very special statement that appears in section 4.4 on page 225. That tells us, well, the fourth elimination of any matrix can be completed without row exchange if and only if all the principal submatrices are non-singular. Okay. And in this case, if these matrices are all non-singular, then the case pivot number dk so is determinant of AK divided by determinant of AK minus 1. So that is what we got in the previous section. Yeah. Okay. All right. And the assumption from number 3 tells us the principal submatrices have all positive determinant. That means they are all non-singular matrix, right? So my matrix A is satisfying this condition, right? They are all non-singular. Therefore, the case pivot dk, which can be written as determinant of AK by determinant of AK minus 1. But since this number and that number, they are all positive, so dk is still positive. Okay, so pivots are all positive. And finally, from number 4 to number 1. Okay, so because of the assumption from number 4, A has LDU factor. So A has the fourth elimination without row exchange. That means A allows the LDU factorization. In addition, so we are also assuming that the diagonals, the pivots are all positive. So diagonal entries of this middle matrix D, so also must be positive, right? Because, well, these diagonals are precisely the pivots that we obtained from the fourth elimination. Okay, so now we have the LDU factorization of A. And I want to take a transpose of this guy. So taking transpose, now order must be reversed. So U transpose, D transpose, and L transpose. But since this is a diagonal matrix, so this is UT D times LT. And you also need to remember that A is a real and symmetric matrix. So since A is a symmetric matrix, so AT must be the same as A. And also I want you to remember that LDU factorization is unique. And so this is, well, this is the LDU factorization of A transpose. And also we assume that LDU factorization of A was LDU here. And since the LDU factorization is unique, therefore this guy must be L, and D is D, and U must be L transpose, right? Just simply speaking, just U transpose is L. Okay, so, well, therefore, if your matrix A is symmetric, then LDU factorization turns out to be A times L, D, L transpose factorization. Okay? Okay. All right. Now, I want to prove that A is a positive definite. In order to see that, I'll just take any random vector from Rn, and I multiply by xt times a times x. But we know that A is LD L transpose. And I want to declare this vector L transpose X by Y. So this is Y. So, and if this is Y, then XT times L is just automatically going to be Y transpose, right? So this one can be written as YT times DY. And this is YT times DY. So this is YT, this is D and Y. Okay. And well, expanding this, so you get just simply d1 times y1 squared plus da 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 dn times yn squared. And because of the assumption from number 4, we are assuming these diagonals are all positive. So d1 to dn, they are all positive, and y1 squared and yn squared, they are also non-negative. So this is automatically going to be non-negative, right? And under what condition this equality is true? This equality is true. Well, since d1 from dn, they are all strictly positive. So therefore, the only possibility is this equality is true only if y1 from y1 to yn, they are all equals to 0, right? So equality is true only if y1 and yn, they are all equals to 0, right? So in other words, y is the 0 vector. Okay, but also, do you remember the shape of the lower triangular matrix L? So L of the matrix L was a lower triangular matrix whose diagonals are all ones, right? So L is a non-singular matrix, therefore L transpose must be also non-singular matrix. And being non-singular implies if and only if its null space is the trivial space. Therefore, y equals to 0, that forces x must be 0 too, right? So x equals to 0. So in conclusion, the equality is true only if x is the 0 vector. So that means this is the matrix A is positive definite. Okay. Great. Okay, so before I move on, so going back to the statement. So we have basically 3 different criteria that tells us if any given real symmetric matrix is positive definite. Well, this is a digression, but with the last year, so when I was teaching the multivariable calculus course, then so I tried to mention the notion of Hessian. Then how do you find the Hessian is positive definite? Then I remember that I gave my student criteria number 3. So if you can compute the determinant of all these principal submatrices, then you know if your Hessian matrix is positive definite, and you can find out if that critical point is the local minimum. But now I recall that was actually not a good idea. Why? Because in order to enforce the criteria number 3, then you are supposed to compute the determinant of n many different matrices, right? Which is not great because a computation of a determinant will require an algorithm whose time complexity is n factorial, right? And so, well, in terms of computation, I think condition number 4 is better than condition number 3 because it just involves the fold elimination, and fold elimination has the polynomial time complexity, which is significantly better than the determinant. Okay. Okay, so end of digression. Sorry. So, so we now have 3 criteria to tell the being positive determinant, but just one more criteria to go. Another criteria. So this theorem also tells us another criteria that tells us if any given matrix is positive definite or not. A real and symmetric matrix A is positive definite if and only if there is a matrix R with independent columns such that A is R transpose times R. Oh, by the way, so if you take a transpose of this RTR, then you can easily realize that RTR is automatically a symmetric matrix, right? Okay. Oh, also this is very interesting fact that R doesn't have to be square matrix. R can be any square matrix, right? And so R can be any rectangular matrix. Oh, sorry, not any, but R must be always, so R can be square, but R can be also narrow matrix, right? Right, yeah. I mean, so just ignoring the size of matrix R, but if you can find at least one matrix R satisfying this, then that means A is a real symmetry. Okay. Okay. The proof. Which side is easier? So I believe this direction is easier. So let's do this. Suppose that I was able to find the matrix R, which has independent columns and such that RTR is matrix A. Now choose any random vector X, and I want to compute this xt times A times X, but replacing this A by RTR, and xt RT can be written as R times X and everything transpose. And this is what? This is just simply inner product of vector Rx, right? And the inner product is always non-zero, right? So this guy is always greater than or equal to 0. Okay, so it remains to show that this equality is true for only if when X is a 0 vector. But this is very easy to see because this equality is true only if the Rx is the 0 vector, right? But well, now this condition kicks in. That is, R has independent columns. If your matrix R has independent columns, that means the null space of the matrix is always the trivial space, trivial subspace. So Rx equals to 0 and R having trivial null space implies Rx to 0 implies that X must be 0 vector too, right? So therefore, the equality holds only if X equals to 0. Right? So that also implies that A is a positive definite matrix. Okay. Good. The other direction. Sorry. Excuse me. Okay. Now, suppose that A is positive definite, and I want to consider the LDU factorization of the matrix A. Well, in this case, since A is the real and symmetric, so LDU factorization actually turns out to be LD and L transpose factorization like this. Okay. And since A is positive definite, these diagonal entries from D1 to Dn, they must be always strictly positive, right? So Di is greater than 0 for all i's from 1 to n. Okay. Now, I want to do something crazy to this middle matrix. I just want to factorize this middle matrix like by this guy times that. So this matrix is, well, this matrix is another diagonal matrix, but whose diagonal entries are just taken by, well, obtained by taking the square root of these diagonal entries, right? Then this guy can be written as the product of these two matrices. Well, I tried to go. So I tried to figure out the names, give the name of this matrix, but I cannot think of any better name than square root of matrix D. Yeah, it sounds very crazy to taking a square root of any matrix, but well, this is just name. So I cannot think of any better name than this. So this is L square root of D. Yeah, that's what this is, but still, this is still another diagonal matrix times, well, square root of D times L transpose. But you know, the square root of D times L transpose can be also written as L times square root of D and everything transpose, right? And this matrix L times square root of D, this is clearly a non-singular matrix. Why? Because this matrix, the square root of D, is a diagonal matrix whose diagonal entries are always all positive. So D is a non-singular matrix, and L is also non-singular matrix, right? Because the L is a lower triangular matrix whose diagonal entries are all ones, right? So L times square root of D is non-singular. Therefore, its transpose must be also non-singular too, right? So, and declaring this guy to be my R, then I have RTR factorization of my matrix A. Right? Okay, good. So this entire discussion can be summarized by in the name of Cholesky, the mathematician. So this is called the Cholesky factorization or Cholesky decomposition. So that is every positive definite matrix allows there is a lower triangular matrix L such that A is L times L transpose, which is precisely this. So this is lower triangular matrix and the lower triangular matrix transpose. So this factorization is called the Cholesky decomposition. I need to tell something more about this decomposition. Well, going back to the theorem. So A being positive definite if and only if I can find such a matrix R. But you have to remember that such a choice of matrix R may not be unique. Well, the Cholesky factorization is the one way to obtain such a matrix R, but you can find such a matrix in different manner. Like, well, since A is the real and symmetric, therefore it can be orthogonally diagonalizable matrix. So, well, A can be written as the orthogonal matrix Q times the diagonal matrix lambda times Q transpose, right? But if you take the square root of this diagonal matrix lambda, you know, so since A is positive definite, so its eigenvalues are all positive, right? So taking the square root of this middle matrix lambda still makes sense, right? So Q times square root of lambda times square root of lambda times Q transpose, and you can write like this. And this is the another way of getting your matrix R, satisfying such a factorization. Okay. Okay. Semi-definite matrix. Okay. I think I have introduced the semi-definite matrix in my previous lecture. So semi being a real and symmetric matrix is semi-definite is a slightly more relaxed condition than being positive or negative definite. Well, this is the definition. A matrix is, well, a real symmetric matrix is positive semi-definite if xt times a times x is greater than or equals to 0 for all vector x. So you can see the condition that the equality is true for only if x is 0. That condition was dropped. So because in this sense, I say this is the more relaxed condition. And you can still define the negative definite matrix in the same way. And this is the theorem. This theorem tells us the criteria, the 4 different criteria that tells us that A is positive semi-definite. So, and I will just give some time to read the statement from number 1 to number 5. But I don't feel like I will need to spend another time and effort to prove the same theorem. So the proof is uses almost the same idea. So I don't feel like I will need to prove this theorem one more time. Okay, good. Yeah. Great. Great. This is very interesting application regarding the ellipsoid. You know what ellipse is, right? The squeezed circle. That is ellipse. Well, ellipsoid is if you're considering the ellipse in the higher dimension, then we say that is an ellipsoid. I say in my dictionary, this is 2-dimensional ellipsoid embedded in R3. So why is it 2-dimensional? Because, well, as a surface, it is a 2-dimensional entity. I should be saying manifold, but no, never mind. So this is 2-dimensional. In my book, this is a 2-dimensional ellipsoid embedded in the 3-dimensional Euclidean space. Generally speaking, so n-1-dimensional ellipsoid embedded in n-dimensional Euclidean space is given by this equation. Okay. And even though you may not be able to draw the picture of this, but you can still identify, for every ellipse or ellipsoid, there is a major and minor axis. And you can also specify the exact length of each of these axes, right? Just by looking at the theorem, right? 그렇죠? 그렇죠? You know how to find the length of the major and minor axis of ellipse. Okay, okay, good, great. Yeah, that's good. Thank you. Okay. All right. So now I am interested in drawing the graph of the ellipse. But the question is, you can easily draw the graph of this ellipsoid in Rn, but if your quadratic equation on the left-hand side contains a term which contains that x1 times x2, then now things are getting more and more complicated. For instance, try to draw the graph of this quadratic function equation. Do you think you can draw this? This guy. Well, of course, if you have the graphing calculator, then it doesn't matter. It is not a problem at all. But, well, if you provided that you do not have any graphing calculator, then drawing the picture graph of this guy will be somehow complicated. Why? Because this quadratic equation involves the term that contains u times v, right? So you cannot identify the major and minor axes and the length of their axes. So how do you draw the graph of this one? All right, so and the idea is a real and symmetric matrix. So So this is the idea. This is the right hand, sorry, this is the left hand side. And I divide this coefficient by 2. So 2 times 4 times UV. And by doing so, reading each of these numbers, 5, 4, and 5, I can think of a real and symmetric matrix A that looks like this. So this equation is the same as this, okay? And since this guy equals to 1, and we are assuming that this guy also equals to 1, okay? And I'm gonna call this guy A. And this is a real and symmetric, and because of the spectral theorem, so this guy can be diagonalized. You need orthogonally diagonalized. So spending enough time and effort, then you can easily realize that it has 2 eigenvalues. The one is 9, and the other one is 1. And you can also find the eigenvectors of each of these eigenvalues. And because of and I am assuming that all these eigenvalues have length 1. So these are my eigenvectors as corresponding to these eigenvalues. Okay. So this is always possible because, well, spectral theory. Okay. So, well, now we have the eigenvalues and eigenvectors, so we can diagonalize the matrix A, this middle matrix. So this equation is now U times B, and this vector and that vector, and this middle matrix, which is now diagonal matrix, and this guy transpose times column vector UV is 1. Okay. All right. Okay. Now things are getting interesting. Oh, okay. This middle matrix here, it just carries over down there, and I multiply this guy, this matrix by this row vector by this matrix. Then, right? So 1 over square root of 2 times U plus B, and 1 over square root 2 times U minus B. And here, so taking transpose, then this is 1 over square root of 2 U plus B, and 1 over square root of 2 U minus B. You must be able to realize that the first entry of the first entry and second entry of this row vector is always the same as the first and second entry of this column vector. Okay. So, and I am now writing this guy, expanding this guy as 9 times, since this and that entry, they are identical. So this guy times this number squared plus this eigenvalue times this guy squared. What makes this expression interesting? Because this matrix in the middle, whose off diagonal entries are all 0, right? Because this is diagonal matrix. So then let me just declare this guy, this parenthesis, this expression in this parenthesis to be my large U, and this guy to be my large B. Okay? Then eventually I get another equation, another quadratic equation, but this is 9 times large U squared plus 1 times large B squared equals to 1. And as you can see from here, since this is diagonal matrix, it does not involve any term that has U times V. Right? And I strongly believe that you can draw the picture of this guy because it doesn't involve any term of U times V. So, what do we know here? So drawing this guy, the graph of this guy, U is the major axis of this ellipse is in the direction of the V axis, right? Whose length is 1, and the minor axis of this ellipse is in the direction of the U axis, large U axis, whose length is 1/3. Agreed? Yes? Okay, but hey, hold on. What is my u and v axis? Because, well, originally the question was given in the small u and small v axes. So my final answer should be also drawn in small u and small v plane, right? So how do you identify large u and large v axis? Well, you know, in our traditional x and y axis, the x-axis can be characterized by y equals to 0, right? And the y-axis is characterized by x equals to 0, right? So in order to obtain the u-axis, I will need to set, in order to get the large u-axis, I will need to put this large v equals to 0. Large v equals to 0 implies small u is the same as small v. So this is my large u-axis in small u and small v plane. Right? What about large v-axis? The large v-axis is characterized by large u equals to 0, and large u equals to 0 if and only if small u plus small v equals to 0, which is precisely this line over here. So this one must be the large v-axis. And so and these two axes, they are orthogonal to each other because we diagonalize this guy. Well, because these two eigenvalues are orthogonal to each other, right? So this is my large u-axis and this is my large v-axis. And according to this last equation, the major axis was in the direction of v-axis. So this ellipse, so the length of this guy, the length of this major axis should be 1. And length of this minor axis should be, in the u direction, it should be 1/3. Just like this. Okay. Okay. Great. Okay. Even though this exercise is everything is in about the 2 dimensions, but I believe you can easily generalize this technique in higher dimensional cases, right? Oh, sorry, just one more thing. So, well, every quadratic equation can be written as x times the matrix times another column vector, right? But, and we got the ellipse. We get the ellipse because the eigenvalue, these two eigenvalues are all positive, right? But what if you have some negative eigenvalues for this real and symmetric matrix? If you have a negative eigenvalue, then your picture should be not an ellipse, but should be something more like a hyperbola or hyperboloid. Okay? So that depends on the signs of the eigenvalue. All right. So this entire discussion can be summarized by this theorem. And suppose that if A is positive definite matrix with eigenvalues from lambda 1 to lambda n, then and because A is positive definite, so lambda 1 to lambda n, they must be all positive, right? And the equation, this quadratic equation, xt times a times x equals 1 can be simplified to lambda 1 yn squared plus lambda 2 y squared plus lambda n yn squared equals to 1. And in this case, each of these y's are actually qt times x1 to xn. Okay, qt times x1 to xn. Okay. Good? Great. The law of inertia. Okay. Now we are facing one of the most important questions on the positive definite matrix. So in this section, so we are mainly interested in real and symmetric matrix. But why are we so much interested in the real and symmetric matrix? It has more crucial. There is a more crucial idea lurking underneath. Well, simply speaking, in my opinion, the real and symmetric matrix is very important because it can represent a so-called a symmetric bilinear form. Okay, so what is a symmetric bilinear form? This is the definition of the symmetric bilinear form. A symmetric bilinear form is a function which takes two vectors as an input and will give you and will return a one real number, satisfying these conditions. So what are these conditions? First, it must be symmetric. So B of VW is the same as B of WV. So you are always free to interchange these two vectors. And condition number two is for each of these, for every position, it must be linear. So A V times BW, comma U is A times B VU plus B times B WU. So therefore, this B must be linear in this position and that position. This is what we call a symmetric bilinear form. This notion of a symmetric bilinear form appears in so many different contexts in mathematics. Like, if you're working in some, I'm a geometer, so yeah. All I can think of is some example regarding geometry. But in general relativity, so you are always concerned about some metric. Metric is a very special type of the inner product. Inner product is one special and important example of this real symmetric bilinear form. Okay, and also in general relativity, the metric is also a symmetric bilinear form, and also in some in many homology theories, I forget it. So it is important in mathematics. Just take it as. I'm sorry. So we are interested in the symmetric bilinear form. A symmetric bilinear form can always be represented by some real and symmetric matrix. Real and symmetric matrix. So this is the idea. Sorry. If you just choose a basis of the vector space Rn, and once you choose the basis, then you can represent this symmetric bilinear form by some real and symmetric n by n matrix. But that means if you choose two different bases then even though your symmetric bilinear form remains the same, their matrix representation might be different. Okay, so how do you then, the question is, how do you know two different real and symmetric matrices are representing the same symmetric bilinear form or not? This is very important idea in this context. Actually, we have encountered such a question, a very similar question in linear transformations, right? So once the linear transformation is given, then we were able to represent that linear transformation by some matrix by choosing the basis, right? Choosing a basis, then you can have the matrix representation. But that means if you chose two different bases, then the matrix representations of the same linear transformation might be completely different. And two different matrices are representing the same linear transformation if and only if they are similar to each other, right? That is why we care so much about the similarity transformation. And the same thing is true. Same thing is true here. The idea is this. First of all, I will need to give you the definition of the congruence transformation. Well, A is a real symmetric matrix, and a congruence transformation of A is CT times A times C for some non-singular matrix C. In this case, A and CTAC, they are called congruent. And also you have to notice that this guy, if A is real and symmetric, then CTAC is again real and symmetric, right? So therefore, this notion of the congruence transformation is working in the world of not every matrices, but in the world of the real and symmetric matrix. Okay. Okay. So, all right. So let me go back to the symmetric and bilinear form. Let us consider this scenario. Well, suppose that the symmetric bilinear form B is fixed, given. Now, we choose the basis of this vector space Rn. Then, once the basis has been chosen, then symmetric bilinear form can be represented by a matrix. So here I have chosen a basis, which I will call the curly B1, which consisting of E1 to En. I'm sorry, so I realized that my choice of notation was not great because I usually reserve these notation for the standard unit vectors, but in this context, then they can be just any random basis vectors. So, just say I have chosen some random basis of Rn, then for any two vectors x and y, so they can be written as a linear combinations of these basis vectors, like this, okay? So I plugged in these vectors x and y into my symmetric bilinear form B, and so x and y can be replaced by these two summations like this. And since B is a bilinear, so because I was feeling lazy, so I just combined these two summations into one. So this indices I and j is varying from 1 to n, and AI times Bj times symmetric bilinear form of these two basis vectors. Okay. All right. Now, by the way, if you're looking at my lecture notes that I uploaded earlier, then you can see that I forgot to put the indices in this middle matrix. So this is the right lecture note. So I'm gonna upload it after the end of this lecture. So, but anyway, the thing is, even though this one looks somehow messy, but I try to organize as much as I can. So I put this row vector A1, A2, AN. So these numbers going here, and this is now going to be n by n matrix, and this number bj's from 1 to n, they appear over here as a column vector. Then just try to multiply these matrices. Then I am pretty sure that you will end up with precisely this expression. So A1, A2, so A1, this guy times that is going to this. Okay. Yeah, this guy, so this index I matches to this first index over here. Yeah, this is great. So this is right. Good. So, therefore, this symmetric bilinear form, all information on this symmetric bilinear form is actually contained in this middle matrix, right? Because to understand symmetric bilinear form, all you need to know is symmetric bilinear forms between basis vectors. Then you can completely determine the symmetric bilinear form of any two vectors. So this middle matrix over here is called the matrix representation of the symmetric bilinear form B with respect to the basis curly B1. And also you have to notice that this middle matrix is symmetric matrix. Why? Because this symmetric bilinear form is symmetric. Therefore, B of E1 and En is always the same as B of En and E1, right? So this middle matrix always must be symmetric. So the idea here is every symmetric bilinear form can be represented by a real symmetric n by n matrix once the basis has been chosen. Okay. Now, I want to choose a different basis for the same vector space. So this time around, I have chosen different bases. I'm going to say they are just from F1 to Fn. And this is a basis curly B2. And since I have chosen new bases, and so therefore the previous basis vectors EI can be written as a linear combination of these F vector, basis vectors F. Okay. So this number can be understood as a, well, if you write down these numbers in two-dimensional arrays, then that's going to be a change of basis matrix. Okay. So, well, previously my X was written as a linear combinations of the basis vectors E's, but since if you replace this EI by this expression, then you're gonna get that expression for the same vector X. Well, again here, so because I am feeling lazy, so I just combine these two summations into one. And Y, the vector Y, which was previously written as a linear combination of E, well, again, was written as a linear combination of F. Okay. BK, CK, okay. All right. So now I'm going to compute the same thing. B of X and Y. Then X is this ugly notation, and Y is that ugly notation. And these two expressions going here and there. And okay, since they are linear, so this summation is now taken out of this parenthesis. Now I have this ugliest summation you can ever imagine. So, well, in this indices, IJKL is varying from 1 to N, and AICIJ and BKCKL, and times symmetric bilinear form of the basis vectors FJ and FL. Okay. All right. Okay. So even though this one looks so ugly, but I also try to organize this expression as much as I can, and it turns out to be this one. So this guy goes to here. So numbers A1 to AN, and these numbers going there as a column vector, and this Cij. This Cij. Okay, so this index is this one. Okay, good. But this is, now we want to consider this guy to be a column vector. So, okay, so this number and that number must agree. Okay, so this is the right, this is the right expression. B1. Okay, right. Okay, the thing is, you should be able to realize that this guy is precisely the transpose of this matrix. Okay. Okay. Now what? So I have computed the same symmetric bilinear form of X and Y, and previously I have this one. This matrix was called to be A, right? This matrix representation was called to be A. And this matrix representation, this guy, this matrix in the middle, this matrix is this is a matrix representation of the same symmetric bilinear form, but written in terms of the basis B2, right? And which I will call D. Then it turns out this whole thing is just A, right? So A is C transpose times another real and symmetric matrix D times C. Okay? Okay, so this gives us some idea. So that is, suppose that you have two different real and symmetric matrices of the same size. And if two matrices are similar, congruent to each other, so if you can find some non-singular matrix T, C such that A is CT times D times C, so if those two matrices are congruent to each other, that means if and only if these two matrices are representing the same symmetric bilinear form, only the choice of basis was different, right? So two real and symmetric matrices of the same size representing the same symmetric bilinear form if and only if they are congruent. Okay. Okay. I already spelled out the theorem. So two real symmetric matrices A and B congruent if and only if A and B represent the same symmetric bilinear. So now a very natural question arises. That is, okay, suppose that you have randomly chosen two n by n real and symmetric matrices. How do you know that those two guys represent the same symmetric bilinear form? How, in other words, how do you know they are congruent or not? So, and actually, we have very nice and beautiful answer to that question, which is called a Sylvester's law of inertia. So let me try to read this. Two real symmetric matrices are always congruent if and only if they have the same number of positive eigenvalues and negative eigenvalues and zero eigenvalues. You know, because of the spectral theorem, every symmetric matrices, real symmetric matrices have all real eigenvalues, right? And you do not worry about the exact values of the exact number of eigenvalues. So what you will need to worry about is just you will need to worry about the sign of the eigenvalues. So okay, for example, suppose that you have two by two real and symmetric matrix, and this guy has eigenvalue 1 and 2, and suppose that this guy has eigenvalue 3 and 4. Are they congruent? Yes, they are congruent because the number of positive eigenvalue was 2, and this guy also has positive eigenvalue 2. Number of positive eigenvalue was 2. So they must be congruent to each other. What about this? So this guy, this real and symmetric matrix, which is 2 by 2, has eigenvalue +1 and -1. And this guy has +1 and 0. Are they congruent? No. Because this guy has 1 positive eigenvalue and 1 negative eigenvalue, but this guy has 1 positive eigenvalue and 1 zero eigenvalue and 0 negative eigenvalues. So all you need to do is just count the number of positive and negative and 0 eigenvalues. And if these three numbers are all agree to each other, then you know that they are congruent. Isn't that amazing? Yeah, no. Yeah. Well, at least for me. So when I was a freshman, so I found this one so amazing. And so I try to give you the very concise proof of this theorem. So I read our textbook. I know I'm not in the position of evaluating one of the most celebrated professor in the field of applied mathematics, but I believe the theorem, the proof given in our textbook, is not very accurate. So I tried to give you another right proof of this theorem, but I wasn't able to find any nice and concise proof that fits in my time frame of this lecture. So I decided to omit it. I'm sorry about this, but you just trust me. So this is so. So being congruent is completely determined by number of positive and negative and zero eigenvalues. Okay. Finally, this is very nice, interesting exercise. Locating the eigenvalues of A. So, eigenvalue is very important, but unfortunately, we do not have that many nice computationally stable algorithms to find the eigenvalues. Why? Because in order to find eigenvalue, then in principle, you are supposed to compute the characteristic polynomial. But in order to compute characteristic polynomial, then you are supposed to initiate the determinant algorithm, which has the factorial time complexity. So not a good idea. But this algorithm which I will introduce from now on is one of the first successful algorithm, computationally stable algorithm to find eigenvalues of any given matrix. So let's talk about this. So let A be real and symmetric matrix. And since A is real and symmetric, so by the spectral theorem, so A has a diagonalization. So let lambda be diagonal matrix of eigenvalues of A, and D be the diagonal matrix of the pivots of A. And A and D have the same number of positive and negative and zero entries. Why is that? Okay, so let me try to take a look at this. So, this matrix D is obtained by the LDU factorization of the matrix A, because the diagonal matrix of pivots of A, right? So because of the LDU factorization, however, since A is a symmetric matrix, so LDU factorization is in fact LD times L transpose factorization, right? So therefore, the matrix A and matrix D, they are congruent to each other. They are congruent matrices, right? And because of the law of inertia, so A and D have the same number of positive and zero and negative eigenvalues. And by the way, what is the eigenvalue of this diagonal matrix? The eigenvalues of diagonal matrix is the diagonal entry itself, right? So therefore, lambda and D have the same number of positive, negative, and zero entries. Okay. Okay. Now, this is a very interesting exercise. Suppose that I have a real symmetric matrix A. And let us suppose that A has positive pivot. So, we can, but A minus 2 times I has a negative pivot. Suppose that I have this hypothetical scenario, situation. Okay. Now, you have to realize that eigenvalues of this matrix are obtained by shifting eigenvalues of A by -2. Why? So if you do not understand, just take a look at this equation. So this is a characteristic polynomial of the A minus 2i, right? But simplifying this, it turns out this is the characteristic polynomial of A, but shifted by -2. Okay. So every eigenvalue of A minus 2i is just nothing but eigenvalue of A shifted by -2. Okay. All right. Now I know that this guy has some negative pivots. Okay. And that means the minimum so the least eigenvalue of A is less than 2. Why? Because previously A has all positive eigenvalues, right? Because A has all positive pivots. But shifting the eigenvalues by -2, now I have one negative pivot. That means I can, this least eigenvalue is now going to be something in the negative number. So that means the least eigenvalue of A is somewhere between 0 and 2. Right? Okay, so now we have some sort of range, the possible range of the least eigenvalue of A, which is from between 0 and 2. Okay, now let me try to compute the pivot of A minus I. If A minus I have negative pivot, then what does it mean? Shifting the eigenvalues of A by -1, then I can still find the negative pivot. That means by my negative eigenvalues of A, the minimum eigenvalue of A is in the range somewhere between 0 and 1, right? So if not, then that means shifting by 1 does not change the sign of the minimum eigenvalue, right? So that means my minimum eigenvalue is in the range of somewhere between 1 and 2. And so on. So likewise, so if you repeat this procedure, then you can somehow pinpoint the range of the minimum eigenvalue of A. Then you can find, in this sense, you can find the minimum eigenvalue. You can locate the minimum eigenvalue of the matrix A. Well, the great thing in this algorithm is it does not involve any determinant algorithm. So it only make uses of the fold elimination, right? So because it only counts the number of pivots. So it uses the fold elimination algorithm, and fold elimination algorithm has polynomial time complexity, which is significantly better than taking the determinant. Okay. But the downside is this algorithm is only true for the real symmetric matrix. So if your matrix is not symmetric, then well, maybe you need to look for some another algorithm. I don't know. Oh, sorry. My time is up. So this is for today, and thank you for your patience. See you next time.